Hey, my name is Cecilia and I will present our paper Nonisotropic Gaussian Diffusion for realistic 3D human motion prediction. Let's start from the beginning. Human motion prediction is the task that takes as input a past motion and aims to predict the corresponding future. In the real world, the future is not deterministic, and there are many different possibilities of how a motion may unfold. The goal of this probabilistic task is to generate futures that are diverse among each other and cover a wide range of motions. Previous works focus in generating motions that are diverse, but not always realistic. For example, not realistic in terms of feasible for the human body, or in terms of plausible and coherent with respect to the input past motion. We propose to address this issue by embedding an explicit inductive bias on the body skeleton kinematic in both the model architecture and the generative process. We present SkeletonDiffusion, a latent diffusion model with a graph attention architecture tailored for the human skeleton and trained with a novel Nonisotropic Gaussian Diffusion formulation. You're welcome to read the details on the architecture in our paper. Here I will tell you more about nonisotropic diffusion and the intuition behind it. Conventional denoising diffusion models are isotropic, meaning that they define the noise transitions between consecutive diffusion time steps as random noise from a Gaussian distribution with isotropic covariance sigma t. More principled, they assume pixels to be identically and independently distributed, so the covariance matrix of the noise is diagonal. Isotropic comes etymologically from ancient Greek and means same behavior in all directions, which here translates into zero values in all off-diagonal entries. In human motion prediction, we're not dealing with pixels, but with human body joints, and a diagonal covariance assumes that there is no correlation between body joints. But in reality, body joints are connected to each other by limb and bones. These connections are known and given by the adjacency matrix of the skeleton graph. We assume the connectivity to be indicator of correlations, and thus obtain correlations from the adjacency matrix. We first make it positive definite by shifting the eigenvalues to the positive range, and then normalize them between 0 and 1 to ensure the noise magnitude is comparable with the isotropic case. In this way, we obtain a suitable correlation matrix that can be integrated into the diffusion process, which is now non-isotropic. While the simple formulation already outperforms the isotropic counterpart in our experiments, we observe that the generation process starts by defining a core structure and later refines it with fine-grained details, meaning that non-isotropic noise becomes more relevant in the later diffusion stages. According to this finding, we add a scheduler gamma t to blend isotropic and non-isotropic noise, resulting in the final non-isotropic formulation of skeleton diffusion. From this definition of correlated noise, we derive not only a sample paradigm, but a whole training and inference regime. Looking at the experiment results, skeleton diffusion reaches state-of-the-art performance with significant improvement in precision and realism. We conduct extensive experiments on multiple datasets involving motion capture data, nosy data from visual sensors, and zero-shot in the wild conditions. Here are some qualitative results for the example we saw in the beginning of the video. Try out our demo nagging face for more results. During the experiments, we introduced body realism metrics to demonstrate previously overlooked issues. We showed that motions exhibiting limb stretching and twisting tend to numerically affect the diversity score, resulting in the undesired phenomenon that gives better diversity scores to unrealistic motions. Other insights are delivered by ablation on the diffusion formulation within our framework. Our non-isotropic diffusion outperforms the conventional isotropic counterpart. An intuitive explanation is that the inductive bias on the skeleton structure eases the learning task for the model, so hyper performance is reached with fewer parameters and less training iterations. Since our covariance matrix is neither learned nor sample dependent, these benefits come at no extra computational cost. Interesting news, our non-isotropy formulation is general and can be applied to other problems beside human motion prediction. Try it out! For the code, pre-trained models, more results, and the Hugging Face demo, visit our website. Feel free to give our GitHub repository a star. Thanks for listening.